Hi guys, let's learn some more electronics on with electronics repair. If you've been watching the previous videos and following the series, you know we've talked about inductors previously. Inductors are coils of wire, and we had a look at how these work. So if you didn't watch the video on inductors, please go and watch that, otherwise this may not make a lot of sense, okay? Today we're going to look at transformers. These are not some toys that came out in the 1980s and used a word that was already in common use. Yeah, silly people. But anyway, transformers. So a transformer is two or more windings around the same core, apart from when it's one winding, because it's a little special type of transformer, which we'll talk about. But the most commonly transformers have at least two windings. So here is a transformer. You can see this has two windings around it. This one has more turns of thinner wire. This one has less turns of slightly thicker wire, okay? Now this might look like copper wire, but if we just use copper wire, effectively all the turns would short to each other, because wire is wire, yeah, it's metal. So this is a coated copper wire. It's called enameled copper wire. It has a clear coating on it. Sometimes it can be coloured actually. And the coating is an insulator, so that when it's wound around the core like this one, the turns are insulated from each other, although to the naked eye it looks like it's all shorted together. Okay, we can see these are wound around this metal core. This is made of iron. The sheets of iron laminated together. Okay, so that is a transformer. Here is a slightly larger one. This is marked with some voltages, so it says 220 volt, 12 volt. And this will tell you straight away what a transformer actually does. It changes the voltage and current between the two windings. So this one, we can have 220 volts coming in and we will get 12 volts coming out. We'll talk about that in a moment, but that is another transformer, okay? The same sort of thing, laminated metal sheets with the windings wrapped around it. Okay. Some transformers will be much larger, like this one. This is a pork pie or toroidal transformer. Okay, but it's the same basic thing. We have a donut shaped core, magnetic core, and we have windings wrapped around it. This one you'll see has more windings, so we have one winding here, we have some more here, so there's more wires on this one. Of course we will talk about that shortly. Here is a last one. So again, this one has lots of windings on it. You can see there's lots of wires here. Each set of colours is basically a separate winding on these. You'll see some of them have three, like the blue, black, blue there. Again, we'll talk about that in a moment. So that's another transformer. This one, you can clearly see that the core is made from laminated iron sheets. Okay, all these transformers I've shown you so far have something in common, but there is more than one type or family of transformers. So I will show you another one. Here you can see this is much smaller, but has very thick wires on it. Again, you can see here the enameled copper wire. These are all soldered together, and we can see very thick wires coming to these pins. Okay, these are a little bit thinner. You can see these are a little bit thicker. Okay, and the last one, very similar to that one. Again, we have all these connected together. We have some thick wires on here. Look, red. I told you some were different colours, the enamel. I've seen blue and green and yellow as well, and some more. So what's the transformer actually doing? What happens when we wrap coils of copper wire around the same core? Well, we saw on the previous video using a relay, and again that's just a coil of wire wrapped around a core. When we pass a current through the core magnetizes, and in this case moves the switch, okay, and moves the contact. So we've already seen that passing a current through a coil creates a magnetic field. But the same is true the opposite way around. Moving a magnetic field around a coil creates electricity. And we can easily prove this. I've connected an oscilloscope to this relay coil. Okay? It's connected to the coil. So if I take a magnet and hold it next to the coil, you'll notice a slight disturbance, but nothing really happens. What if I move the magnet? So hold it close to the coil and I'll move it. Look. While the magnet is moving, I'm getting a voltage in the coil. Yeah. If I move it slower, it's there, but less. If I move it faster, you see it, yeah? And the frequency of that signal, that alternating current, depends on how fast I move the magnet. Okay, move it slower, move it faster. Okay, and you'll also notice for a faster movement, the faster I move it, the more voltage I get in the coil. Okay, so we can see that magnetism will create electricity when the magnetic field is moving or changing, and that's the important thing. So on our transformer we have two windings. Okay, magnetic core, winding, and we know that a coil will create a magnetic field if we pass current through it. That's what the relay was doing. So if we pass a DC current through here, plus minus, what will happen? Well, when we first switch on for an instance, as current flows through here, the magnetic field builds up, we'll see a voltage on the output. And that's because the magnetic field is not only passing through the windings of this coil, it's also passing through the windings of this coil. But that will only happen while the magnetic field is building up. Once the magnetic field reaches its maximum level for the current flowing through it, the transformer is saturated, the magnetic field doesn't move anymore, it's now static, so there's no change in the magnetic field moving through this coil, and we stop seeing voltage on this side. But as we saw with the magnet, if we move the magnet, we can get a continuous change in voltage here. So to do that electrically, instead of using the plus and minus, we're using AC voltage here. This is continually changing, positive, negative, positive, negative. And that will cause the magnetic field to expand, collapse, expand in the opposite direction, collapse, expand in the first direction, collapse, opposite, collapse, and so on. So the magnetic field is moving backwards and forwards. And the rate at which it's doing depends on the frequency of this AC signal. The higher the frequency, the faster it does it. That then causes a continually moving magnetic field, like I showed you by moving a magnet, to create a voltage here. And coming out, we have the same thing. Sine wave. Now the frequency is the same between this electric AC current and this one. The voltage we get here will depend on two things. One is the frequency, and we'll talk about that a little bit later, but the other one is the ratio of turns. So if this winding, and let's call them something now. This is called the primary. This is the winding that you're driving, you're putting power in. And this one is called the secondary. This is the winding you're taking power out. Okay? Let's say the primary had 1000 turns of wire on it, and the secondary had 100 turns. Okay? So there's 10 times as many turns of wire on the primary as the secondary. What you'll actually find is, because there's less turns of wire, you get less voltage coming out. And the ratio of the turns is directly proportional to the ratio of the voltage. So if we put 240 volts AC in here, this has 10 times less turns, so you'll get 24 volts AC coming out. Yeah? Now the first thing you might think, and you'll be correct, energy can be neither created nor destroyed. So if we've got 240 volts going in and only 24 coming out, where's the other 216 volts gone to? Yeah? What's happened to the other 216 volts? Are they hiding in the corner somewhere? Have they snuck into the metal core? No. The power in and the power out have to be balanced. So if we're passing in here, for example, 240 volts at 1 amp, we can draw out of here 24 volts at 10 amps. Okay? 240 times 1 is 240, and 24 times 10 is 240. And this has a unit, a value, and it's called VA, volt amps. It's very similar to watts. Without going to the mathematics, if you like, you can consider it as watts, but it's technically called VA, volt amps. Go into the comments below, guys, and talk about that. But from a understanding point of view, it's like watts. What current will flow through the primary of your transformer? Well, it depends on what current you are drawing. So if you put a load on here that will draw 20 amps, you now have 24 volts at 20 amps. So you have 480 VA. The current on the primary will go up to 2 amps. Yeah, 240 times 2 amps equals 480 VA. It always has to balance. If you reduce the current you are drawing, the supply current will reduce. So if you put no load on the secondary, will you get no current in the primary? No, you won't, because there's an efficiency of this. So the efficiency basically is due to the fact that this coil of wire, although it's an inductor, it also has some resistance, and it will pass some current even if you're drawing no current on the secondary. So you will not have 0 amps going in if there's 0 coming out. You'll have some going in and nothing coming out. Where's the rest of it going? Well, the transformer warms up. Yeah, it goes into heat. Heat, why? Because the resistance is effectively electrical friction. And you know, with friction, if you rub like a brake pad against a wheel, it will get warm, it will get hot. So although the input current depends on the output current, you have to just always remember there is a loss due to efficiency or the lack of it. Yeah. What happens if you try to draw more power from the secondary than the transformer can handle? Well, what actually happens is normally the primary will burn up because it's a thinner wire, and that's for a transformer that's reducing the voltage. So there is a limit to how much current you can draw, which is effectively how much current the windings can handle. A transformer that's doing this is called a step down. And the first transformers I showed you, like this one, these are mains frequency transformers, which means in North America, 60 Hertz. That's the frequency of the AC. In most of the rest of the world, 50 Hertz, 50 times a second, okay? We can, of course, have a transformer. Didn't draw that very well, did I? But it's a transformer. AC coming in. Secondary, I'll draw it better this time. AC going out. In, out. That has, for example, 1000 turns on here. 1000 T, yeah. And that's 10,000 turns on this one. What will happen now? Well, the same thing will happen. So if we put 240 volts into our 1000 turns, we'll get 10 times as much, 10 times as many turns coming out. So this will now be 2400 volts or 2.4 kV, kilovolts, okay? But we have to balance the power. So now it's the other way around. For every 1 amp going in, you get 0.1 amps on the output. So if we draw on here 0.5 amps at 2400 volts, the input current will be 5 amps at 240. They have to balance. Okay? So that's basically what a transformer does without going much into the mathematics of it. We get various other types of transformer. I'll just show you this. So we can have a transformer primary, okay, and we can have more than one secondary. And the secondaries can have different numbers of turns on. So if this has 1000 again, and this one has 200, and this one has 100, then this will give us, for 240 volts going in, this will give us 24 volts, and this will give us 48 volts at the same time. Okay, and we can add another winding if we like, all on the same transformer. This could be center tapped, so there's like a wire coming from the middle of the coil, okay, an extra wire. This one might have, for example, let's say 100 turns here and another 100 turns here, okay, turns. And what we'll have from here now, we'll find this is 24 volts and this is another 24 volts, and they're connected together at the center point, okay? And across the two would be 48 volts. This is called a center tapped, and it doesn't have to be center tapped. The tap could be somewhere else. So it could, for example, be 300 turns and 100 turns, giving different voltages, okay? You can also get transformers like this. 1000 turns, 1000 turns, okay? 240 volts, 240 volts. What use is that? Because whatever voltage we put in at whatever current, we get the same voltage at the same current coming out, less the efficiency loss, which causes the transformer to warm up. So this looks like it's doing nothing useful other than wasting a bit of power. But what this is doing is actually something very useful. So this is called an isolation transformer. Without going absolutely into the details, if this is your live and this is your neutral coming in, yeah, or you've got one of these EU plugs which you can plug in either way round, so you've no idea which is the live and which is the neutral. You can't connect either of these to ground, the live or neutral. They're either end of a winding, they're not ground. But you might want to ground your equipment, and what you can do is with the secondary, you can connect this to ground. And now this is live, okay? And one end is grounded. Or even more useful, you can connect this to nothing. The reason this is very useful in electronics repair is because if you happen to touch one of the AC terminals, what you're doing is you're adding a human. Okay. Funny looking human, I know. But humans come in all strange shapes and sizes. We know this, okay. So you're adding a human from here to here. And a human is just a resistance. Your skin resistance. So what you're doing in actual fact is adding a resistor. And because you were standing on a patch of mud with no shoes on, because it's a sensible thing to do, the other end of the human is grounded, okay. What happens when you touch that? Well, nothing untoward happens, because this end of the winding becomes ground. The voltage between here and here is no difference, and that end of the winding becomes the live AC. But if you let go of this winding and touch this one instead, okay, you're just adding your resistance here. This end now becomes ground, and that end is the live, which means that you can actually touch either side of the mains voltage without hurting yourself. You won't feel anything. You will not know you've done it. And that's because it's isolated. And this applies to all sorts of transformers I've shown you so far. And this is called galvanic isolation. Okay. And not only is it protecting you, but you could connect something like a grounded oscilloscope to here, or a grounded computer to here, or to here. As long as you're only connecting to one at a time, you can do that, and neither you nor your equipment will come to any harm, okay? The only proviso, if you connect your grounded computer to here, don't touch that one with your finger. You can't have them ground on both ends at the same time, okay? There's one other type of transformer I'm going to mention, and there are a few more afterwards, but you can get transformers with just one winding in. So you can get a transformer like this. So again, this is your AC, 240 volts. And then you can have a wire tap from here. Okay, that connected together. And this is AC. And depending on where you put the wire tap, and the same applies, the ratio in turns. So if there are 9 times as many turns here to the one there, 1 times to 9 times, you'll get 1/10 of the voltage coming out here. Okay, so it's the ratio of turns. So this is also dropping down the voltage, but it's not giving you any isolation from the mains, okay, and it's not allowing you to draw more current than you've got flowing through that, because the only one current flows through all of it, that way or that way, okay. This is called an auto transformer, okay. You can, by the way, get a specialist type of auto transformer. Your 240 AC. Instead of having a fixed tap, it has a slider. So effectively have enamel copper wire, but on one narrow patch, the enamel is missing. The turns won't short together, but you can have a moving slider on this patch. And from here to here, we can have AC out, and depending on the position, it can be anywhere between 0 volts and 240 volts. In fact, normally these things have an extra bit of winding there as well. So you can go down to 0 and up 10% or 15% above the incoming voltage, okay? This is commonly known as a variac. You could make a light dimmer out of this or something like that, but the most commonly used in electronics repair work, where you want to effectively make a variable AC supply to power things up, if they're in a known faulty state, you can work on them without things going bang. But do bear in mind that this will not give you any isolation. So normally speaking, in a workshop, this would go to a isolation transformer, and this would be your mains. Okay, and this would be a 1-to-1 ratio, 240. That's what's set up in my workshop, by the way, and that keeps me pretty safe unless I do something really stupid. Okay, I mentioned that the ratio of turns affects the output to the input voltage of the transformer. I also mentioned that the higher the frequency, the more efficient the energy transfer is. All those transformers I've shown you so far are effectively mains transformers running at mains frequency. These transformers I showed you earlier, these are from switch mode power supplies. You'll see these are much smaller in size, yet often can give as much if not more power than those large transformers I showed you. And the reason is with these is that the primary is being driven at a very high frequency. So you have a very high frequency AC driving the primary, and because of the high frequency, the transformer efficiency is much higher. So the efficiency very much depends on the frequency, and that's why in modern power supplies we find these sort of transformers. It requires more circuitry to drive the transformer primary at the high frequency, and we'll talk about that later in these series of lessons. But for now, just know that that is the way modern electronics normally use transformers. They're much cheaper to make, there's a lot less copper, and they're actually much more efficient as well. So I've mentioned two types of transformer: mains frequency transformers, power transformers, switch mode power supply transformers, SMPS transformers. These are running at, as I say, 50 hertz, 60 hertz, depending on where you live. These are running somewhere into the hundreds of kilohertz, 100,000 hertz plus, sometimes up to 500 kilohertz or up to that. Some will run a bit lower, but that gives you an idea of what frequency these are running at. Old types of switch mode power supplies using things like CRT TVs were running at 15.625 kilohertz. Okay, but these all run at much higher frequencies than these. There's at least a third type of transformer, and then I'm going to hand it over to you guys in the comments to tell me, Rich, why didn't you mention this, that, and the other? Because let's face it, I don't know everything. Okay. The other ones commonly are signal transformers. So these are used for various purposes. Sometimes for a circuit to monitor some external signal, but it needs isolation from it. So you'll have a signal transformer connected between your circuit board and the outside world. For example of that, on things like LAN cables, and similar sort of communication between devices at very high frequencies. Another common use are RF, or radio frequency transformers. These will often have, and I don't have one to show you unfortunately, a little metal can with a variable movable magnetic core that you can move up or down to alter the inductance. Okay, quite often have a symbol like this, variable transformer. These are used again to isolate parts of circuits, but also to let the AC pass. They're also often used in circuits where you have a whole range of frequencies on this side of the coil and you want to isolate a frequency on the other side, so only certain frequencies are passed through. And this is a good example of where you can have transformers with more than one primary. Okay, so this is a very common one. We have 2 primaries, 1 secondary. What happens in this sort of transformer? Well, again, avoiding a lot of maths, and guys, please talk about it. But if you have a whole range of frequencies coming into here, effectively say, for example, of a radio antenna, where you have radio stations across a whole band of frequencies. Yeah. If you feed a fixed frequency into here, AC, it's a fixed frequency. Okay. And in this winding, you have all the different frequencies, example, radio stations on the medium wave band. Yeah. What comes out in this inductor is effectively whatever's induced from here and induced from here. This passing of the current is called induction again, or induced. Okay. The waveform here will actually have 4 things on it. How many things do they have? 4. Okay. What we'll have here is the original fixed frequency we put in here. We call this the oscillator, or local oscillator. Okay, local OSC. So we'll have the frequency of the local oscillator, the LO, local oscillator. We'll have the incoming RF frequency, radio frequency, yeah. We'll have the sum of the 2, this plus this. So that's the sum of LO plus RF, local oscillator plus RF, radio frequency. And we'll have the difference between the 2. Okay, this is the difference between local oscillator and RF. This is the basic principle in which a radio frequency tuner, an analog one, actually works and selects radio stations. And of these 4, the one we're interested in is that one. Because this frequency, which is the difference between the 2, will still contain the information on the RF signal, the music or the voice, but it will always be on the same frequency, the difference between the 2. Okay. So that's an example of the use of a transformer with more than one primary. Of course, there are more. Transformers is quite a wide-ranging topic, but you know what? I think for this video, that is probably enough. So I hope you enjoyed that one. Hope you learned something. Please get into the comments below. Anything that wasn't clear or anything that you think I missed, just let me know, and then if it's of importance, we'll get into the next video. Okay, look forward to seeing you all soon again on Learning Electronics Repair. Ciao for now, guys.